record on this computer. Okay, hello everybody and welcome to our second to last lecture about the diagnostics and about the physics behind Dicke's observations. So as I said, we're going to finish with the Hanle effect, and we're going to mention some off-limb observations today. And then on Tuesday, we're going to talk more about off-limb observations. Aline is going to help us with that. And if the time permits, we're going to take a look at some inversion results. But today, we're going to finish what we started, and that's we're going to talk about the interaction between the vector magnetic fields and the scattering polarization. And I'll spend the first few slides quickly reviewing what we talked about last time. And the last time, basically, we made some sort of phenomenological argument that anisotropy of the radiation field is what determines the amount of scattering polarization, and the sign of scattering polarization as well, right? And we sort of saw a simplified treatment, which at first we employed it for single scattering situations when we had electron scattering or Rayleigh scattering or something like that. And then I sort of extrapolated that more or less blindly to very simple spectral lines, which we usually call resonance lines. And that specific treatment was sort of exact for something called a pure Zeeman triplet, or actually any situation where the lower level is unsplit and unpolarized. Today, we won't quite be able to remedy that. We will see some results and we will see some sketches of what is going on, but I will show you slightly more rigorous theoretical treatment. Still, we won't go super deep into quantum mechanics. We will still stick to the scattering matrices. And we're gonna see what happens when we have a vector magnetic field. And we're gonna take a look at much more results. So there's gonna be slightly less equations and much more plots, images, etc., etc. Okay. So previously what I said is that for the scattering polarization, we're gonna take a different path than we took when we were talking about Zeeman effect, right? When we talked about Zeeman effect, we had these four coupled differential equations for I, Q, U, and V, and we had this huge absorption matrix that coupled these things. However, the source of radiation was purely unpolarized. If you remember, the only Stokes parameter that had the source function was Stokes I. And all the other Stokes parameters were generated from the Stokes I through the absorption matrix or the absorption tensor, right? For the scattering polarization, we have exactly the opposite situation, at least in these simple cases. We have one common optical depth scale, and we have multiple sources of radiation, okay? And that's because here the source function is, and we're going to see it in the next slide immediately, the source function. So here we have the two source functions, one for Stokes I, one for Stokes Q in the most simple case, and these are determined by scattering. So usually whenever, at least in these radiative transfer calculations, when you see this factor epsilon appearing, that means that we're talking about some sort of scattering, and this epsilon is a branching ratio between the thermal and non-thermal sources. And I'm going to spend a little bit more time talking about this because I think that now this sort of sedimented a little bit in our brains, so we can understand this better. And I also fixed the typo that was in the equations in the previous slides. So what I want to stress here is that we have two source functions, one for I, one for Q. So let's start taking a look at the source function for I. We have this epsilon times B, and basically epsilon is, you can understand it as we usually call it photon destruction probability, which is the probability that the energy of the photon in the absorption process will be converted into thermal energy of the gas, right? Which basically means the probability of having true absorption. While obviously 1 minus epsilon is the probability of having a scattering event. Right. And we are usually interested in cases where this epsilon is very small number, something like 10 to the minus 2, 10 to the minus 3, 10 to the minus 4. And for really strong lines, which are formed very high in the atmosphere, it can go down to 10 to the minus 8 or even less. Okay, so it's somehow intuitively clear that the thermal fraction of these processes will contribute to the thermal source function. The non-thermal part will determine the amount of the scattering events. So then we get to these big parentheses here, and here we see two terms. The first term is this J00, which is basically just the mean intensity of the scattered radiation, which is sort of clear for us, but for some reason, also the anisotropy of the radiation, which is some integral given down here, which is basically the same integral as was the one for calculating the mean intensity, just with the extra factor here, 3 mu prime squared minus 1. Also, this anisotropy is going to influence the source function. And more importantly, there's going to be this factor here, 3 mu squared minus 1. So the source function is direction dependent. Okay? And this is very important. Why is that very important? Well, first of all, let's understand the difference between mu prime and mu. So mu prime denotes the direction of the incoming radiation. So to get my anisotropy and to get my mean intensity, I'm integrating over the all incoming angles. To determine the angle distribution of my source function for I and source function for Q, I'm multiplying with these factors for the outgoing radiation, right? And both the intensity and the linear polarization source functions are angle dependent. And there are a few interesting things. One interesting thing is that if mu is equal to 1, the source function for Stokes Q is 0, right? And mu equals to 1 means that for the mu equals for 1 corresponds to the radiation that propagates along Z. And this basically tells us that a Q along Z is going to be 0. And this sort of makes sense because radiation propagating along Z doesn't see any asymmetry, right? Because everything is symmetric with respect to Z, with respect to the atmospheric normal. And this is very interesting thing. This is something that I didn't stress last time and that we see now obviously from these equations here, right? And then another interesting thing here, which we're going to talk about a little bit more, is that in the simplest case, which is the case, actually this is not the simplest case, but in the case where we have the so-called mixed polarity fields that we very often call turbulent or microturbulent, we have these 3 terms here. We have actually this one term here which corresponds to the magnetic field called omega h, which is called Hanle depolarization parameter. But we also have 2 more constants that determine the amount of scattering polarization, WC, which accounts for the collisional processes, and W2, which accounts for something called intrinsic line polarizability. Okay, which depends on the angular momentum quantum numbers of the lower and the upper level. And we're not going to talk into this. This is some number of order of unity. Okay. So this is what we talked about the last time, and then we moved, and then we talked about these things, right? And one interesting thing is that, of course, the source function for Q doesn't have the thermal component, right? Because it purely depends on the scattering process, right? So please know the difference in the formalisms here between this and Zeeman. Of course, eventually we're going to want to have a unified theory, which allows us to treat everything. And there is one like this. It's density matrix formalism, which is described in great detail in the book Polarization in Spectral Lines. Okay. Okay, very good. So one thing that I wanted to emphasize last time and I want to emphasize now is that more non-LT, more polarization, which means more scattering, more polarization. Okay, and then what I also showed you last time is that there are some situations where we have, or we at least assume that it exists, this magnetic field that is mixed on very small scales. And I want you to convince yourself that if we had the magnetic field that is mixed on very small scales, there would be no polarization due to the Zeeman effect. Because Zeeman effect, different orientations and different strengths imply different signs of the Stokes parameters. And when I have things completely isotropic and turbulent in a way, then all these things are going to cancel each other, right? But because Hanle effect, and we're going to see in a little bit what Hanle effect does in the case when we have nice and you know vector magnetic field on relatively large scales, it's going to do something else, right? And the reason why I started talking about the microturbulent Hanle effect is because not because it's probably conceptually more complicated, but it's easier. Simply the equations are easier to implement. You simply have some constant which in a nonlinear way enters in the in this source function for the scattering polarization, and you can calculate everything. And actually it's actually very easy to implement, and if you have some time free, you can probably write a small the two-level atom scattering polarization code and play with these quantities and see how the magnetic field influences your polarization profiles, etc., etc. And this is exactly what was done in this well-known Trujillo Bueno et al. Nature paper from 2004, where they looked at observed scattering polarization at the core of strontium 4607. We're going to mention this line again in a little bit. And what they analyzed were the linear polarization signals and how they are changing along the limb, right? And actually this dependence, this decreasing dependence on mu, is more or less proportional to this thing here. There is more than that. There are some radiative transfer effects and some interesting things, but this mu squared minus 1. So higher mu I have, smaller the absolute value of my Stokes Q source function is, and then I get this thing here, right? And what they found out is that basically some sort of mean magnetic field in the spatially unresolved observations, but still with well-determined limb distance. They found that the mean magnetic field to explain this depolarization is something like 130 Gauss. And it actually agrees very well with magnetic fields inferred from Zeeman magnetometry using observations with nice spatial resolution. Okay, so one thing here is that I forgot to put it in a slide. I probably should, but I think this slide is a very good illustration for that. Is that if you get into this and if you get into all these quiet submagnetic fields, scattering polarization, Hanle effect stories, you're occasionally going to encounter a term differential Hanle effect. Differential Hanle effect basically means that we are looking at we are able to model everything with the unknown magnetic field, and then we see that there is more polarization than we expected, and then from the difference between the observed magnetic field and the theoretical one in the zero field limit, we can infer what magnetic field we need here. And the best candidates for this differential Hanle effect are actually the spectral lines that are very similar in its line formation properties, but have, for example, different sensitivities to the magnetic field or different intrinsic polarizabilities or something like that. And actually, in the molecular lines that I have shown you in the previous class, that was the situation. Okay, because there is a lot of molecular lines and they're all very similar because it's all the same species, but then they belong to different bands and so on and so on. We can talk about this in more detail if you get interested. Okay, but to tell the truth, and which I already did, is that I started with the microturbulent Hanle effect because the equations are simple, right? And it somehow presumes that the magnetic field is mixed and randomly oriented on the scales that are smaller than the photon mean free path, which basically means that photons don't ever see vector magnetic fields, right? And the equations, and now we're gonna go again over these equations and see where they really come from. So the equations that we saw, they come from an approach called scattering matrix formalism. And the scattering matrix is basically a matrix that shows you how the Stokes parameters I, Q, and U change in the scattering process depending on the incoming direction angles, which I denote here with theta prime and phi prime, and the outgoing direction, which is determined with theta and phi. Okay, so this is a matrix, and the reason why Stokes V is not appearing here is that we assume that the initial Stokes V is going to be 0, and then the circular polarization cannot ever be created in scattering processes because there is nothing to retard, right? So we only can have different IQU and their changes, but we cannot have V being created from nothing. Of course, in principle, I could have put V here, but we want to focus on the linear polarization only, right? And so let's say that there is some matrix. I'm not writing the explicit form here, but if you need it, we can look these up, and they are actually a very good introduction if you want to get into density matrix formalism. So what you get here is that there is this matrix which describes you, and in a way it's something like a Mueller matrix, right? It shows you how your Stokes vector is changing in the process of scattering, right? And then, so now we're going to suffer through some equations here. And in principle, it means, and this only illustrates one scattering process. However, we said that we usually work on the ensembles of rays or the ensembles of photons, right? So when I'm looking along the given direction, theta phi, what I see is not only scattering from one direction, I see some fractions of photons scattering from all the directions, right? And what we're gonna, how are we gonna express it? Where we're gonna have some integral. So my total outgoing intensity from the scattering process is gonna be some angular integral of the scattering matrix over all the incoming directions times the incoming intensity over the all incoming directions, right? I hope this makes sense. And then it turns out, it's very good because Marika said yes here when I asked if you hear me, and now whenever I ask, does something make sense, I can look up and I can see her message and it says yes. So that's very reassuring. Okay, so it turns out that this matrix can be written as the product of two matrices, right? One matrix only depends on incoming angles, the other one only depends on the outgoing angles, which means that the part of the matrix or the fraction of the matrix that can be, or the submatrix that depends only on the outgoing angles can be taken out from the integral, and I can create these and I can integrate over the incoming intensity, over the incoming angles, times this part of the matrix which deals with the incoming angles, and I can call this quantity here, let's call it polarized mean intensity or something like that, or radiation field tensor or whatever you like, right? So actually it's not a tensor, it's a vector. This is going to be some sort of vector, right? Because this matrix is, let's say, 3 times 3, the intensity is just 3, and I'm integrating over all the angles, so yeah. So this dependence on angles means that I have matrix, which is 3 times 3, which has different values for different values of the angles, right? Okay. So in one scattering, when I average over the ensemble of all the scatterers, I'm going to get that my outgoing intensity is equal to some matrix which deals with the basically outgoing scattering directions times some vector of mean intensities that I have obtained by doing this integral here. Okay, and the key assumption for this is that this scattering matrix can be decomposed, as we say. Okay, but this is just what happens locally, right? So if from one point my scattering intensity is like this, but when I look down the solar atmosphere, I see contributions of the scattering intensity along all the points when I go down the atmosphere, right? So basically what I have to do is I have to integrate over all this path, and now I'm finally gonna write this radiative transfer equation for the polarized light as the vector equation, right? Where all my quantities here, intensities and the source functions, have 3 components each, IQ, and U component. Okay. In principle, we could also do V, but V would always be 0 because, again, V cannot be created in scattering processes, right? And the source function in general is going to have the combination of the thermal part and the non-thermal part, which is the scattering part, right? And this thermal part, is only going to be non-zero for the I component. For Q and U, the thermal part doesn't exist. It's only the scattering part. And then we can assume what we already assumed implicitly in the previous class, that the atmosphere is one-dimensional, and everything is axially symmetric, or I called it here azimuth invariant. So all the dependency on phi is going to disappear, and so does U, not the Q. Let's fix this straight away because this is really confusing. So does U. That is okay, and so does U. So I only have I and Q, and that's the thing, and I have shown you some of these before, right? And in the scattering, there is no circular polarization once again, so no Stokes V. Okay, cool. So, but there is something that can break the axial symmetry, and that's the magnetic field. So this is, if you get in the Hanle effect, and especially if you get in the prominences and filaments and using Hazel code or something like that, you're gonna go back to this picture so many times. So this here is are a lot of reference systems. Okay, we're gonna take some time to decipher all of them. So first, X, Y, and Z is our atmospheric reference system. So Z is the direction of the atmospheric normal, and our physical quantities are only changing along Z. 1D atmosphere means that. It doesn't mean that our atmosphere is a string. It means that our atmosphere is still three-dimensional. It's just that nothing changes with X and Y. Nothing depends on X and Y. Everything depends only on Z, right? So we have vertical stratification of temperature, vertical stratification of velocity, etc., etc. But now there is a magnetic field which has some orientation, so some non-zero azimuth and some non-zero inclination with the z-axis, and obviously that magnetic field breaks the axial symmetry of the radiation. So think physical parameters: magnetic field, velocity, temperature. Everything still depends only on z, but because magnetic field is a vector, then the intensity depends again only on z, but also on theta and phi, right? And here you have an example ray given with this direction omega here, right? And you have its theta, and here Andres used chi instead of phi. So just keep in mind that this chi here is the azimuth, it's not the opacity or something like that, right? And obviously the rays with different chi are going to have different orientation with respect to the magnetic field and are going to behave differently. Okay, and this, and I'm only going to bump this in front of you now, and we can discuss later if you want it, if you want to discuss it in more details. This is going to change this matrix here, right? This matrix is now gonna depend not only on the angles, it's going to depend on the direction of the magnetic field. And this matrix will be able to create, because of the way it looks, it will be able to create the source function for Stokes U. So the vector magnetic field will, instead of having only I and Q opponent for the scattering polarization, will also, we can say it, rotate some amount of that Q component into U component. So basically, if we allow our atmosphere or our slab or our little blob to be permeated by a vector magnetic field, what we're going to see is the rotation of the scattering polarization. And that is called Hanle effect. Okay? And that is a very, 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 very interesting thing. Okay, I'm just going to leave this here for 10 seconds, and I'm just going to stay in silence, and you try to appreciate what this equation means. I'm just going to stop sharing for a second. Okay, so yeah, this is the briefest way to illustrate what Hanle effect does. And now there is a lot of more complicated stuff which come if you want to treat things in the more detail. And so in a way, classically speaking, the way that people described it or explained what Hanle effect is, it's a precession of the, when I say scattering electrons, it's a bad statement, because it's not the electrons that are being scattered, it's the electrons that are doing the scattering. Because you remember maybe that we could model the scattering process and absorption and emission processes in general as some sort of harmonic oscillations of the electrons, right? So in a way, these oscillating electrons are now precessing because there is magnetic field sort of changing the axis, the quantization axis, if you want. And that sort of creates the different movement of the electron and creates the different polarization state. Quantum mechanically speaking, what is happening is that the magnetic field, which we are now introducing there, is changing the quantization axis. And it's going to change something called atomic alignment and orientation, which is originally induced by the anisotropic radiation field. And then these atomic alignment and orientation influence how your atoms are emitting. And then we can calculate our source functions for IQ and U now. And this is very complicated and very cumbersome, but very more rewarding and ultimately very useful. You learn a lot of atomic physics and quantum mechanics along the way. I didn't do it quite correctly. And I definitely encourage you to, the book is very expensive and hard to find though, to somehow get your hands on polarization in spectral lines by Gidiolandi e Innocenti, which really is a huge book. I mean, we are going to talk about it in a little bit. So this is very interesting and very useful. And what I want you to stress here is that this quantity that we saw before now appears again. And this is something that I'm going to call Lande parameter or something like that, gamma h. Sorry, not Lande, Hanle parameter, gamma h. And it depends on the Lande factor of the line. And we know that the Lande factors of the lines are typically of the order of 1, 1.5, 2, 2.5, something like that. So order of few. We have magnetic field. We have the Einstein coefficient of emission. And we have this constant, which is roughly of order of 10 to the 7. Okay. And what you see here now, that if we had Einstein coefficient, so in a way, the Hanle effect influences more lines that have low Einstein coefficient of emission. And for example, typical values here are something between 10 to the 5 and 10 to the 8. And then it means that in order to get Lande factor of 1, which is something that is very noticeable, Hanle factor of 1, which is something that is very noticeable, you would need a magnetic field for, so for example, for the Einstein coefficient of 10 to the 7, you would need a magnetic field of roughly 1 Gauss. And this equation here hides the answer why we are so worked up about Hanle effect. The reason is because it's sensitive to very, very weak magnetic fields. So look at this. If I get a spectral line with Einstein coefficient of 10 to the 7, my line would be sensitive to the magnetic field. That line would be sensitive to the magnetic field of 1 Gauss. If I had a line with the magnetic field of 10 to the 6, it would be sensitive to the magnetic fields of 0.1 Gauss. Fantastic. Really, really cool. Because remember that when we talked about previously, we had the situations that few hundred Gauss magnetic field would create 1% or something like that polarization. The disadvantage about, so this is obviously an advantage of the Hanle effect. The disadvantage is that to begin with, the polarization degrees are small, as I said, fraction of a percent. Then when I imply the Hanle effect, it's going to rotate and depolarize the scattering polarization, which means I'm going to get even less. And then the theoretical explanation is much more complicated. There are relatively few lines that are sensitive to it, and so it's very hard to observe, and so on. So. But this is something that we are really hoping to harness with the DKIST. And it's really, really something that is very interesting to investigate. Okay, so if you want to fully understand and fully model this, you have to take the path of the so-called density matrix. And using the density matrix, which basically fully accounts for all the interaction between the radiation and the Zeeman sublevels of both the upper and the lower level, it's not very obvious, but what we did just now with the scattering matrix would just take into account the polarization of the higher level, not really of the lower level. But by calculating this so-called density matrix and then using it to describe the orientation and alignment of the Zeeman sublevels of the transition, you could really properly model everything that happens in the spectral lines. And my supervisor, Marianne Forabert, on one situation told me that maybe it would be good to move to the monastery for a bit and read this book. And actually, maybe now the occasion is good because we are not going to the office anyway. But anyway, this book is really something special in the world of solar physics, right? And if I could make an analogy, the density matrix approach is to this with respect to the scattering matrix approach, which we just saw, is like going from the simple two-level atom problem where you just have the scattering term, which is linear, to the full multi-level problem where you have all the level populations and the radiative rates and collisional rates and everything like that, right? And this theory can, with some limitations, account for the full story. Scattering non-LT effects, Hanle effect, Zeeman effect, polarization of the lower level, polarization of the upper level. And what I'm going to do now is I'm only going to be talking about the results and implications of that theory. I'm not going to show you any equations about this because they're very complicated and I don't know them, and it would take us all a lot to go through these things in a meaningful way. And it's maybe a topic for a PhD course on its own, but I'm definitely not the one to teach it. I'm the one to attend it. Okay, so let's move on and see what this implies. And I have shown you this before, and now I hope that you can appreciate this a little bit more. And these were basically 3 panels showing us the path from the completely scattering polarization case, which is the uppermost row, all the way down to the Zeeman effect regime. So when we have the pure scattering and no magnetic field in the spectral lines, we have the lines which are typically absorption lines, right? In the atmosphere, I mean, obviously not like prominences and loops and things like that have the emission lines. The linear polarization is, of course, depending on what we say is positive, what is negative, is only contained in the Stokes Q. And the Stokes U and V are 0 because there is no magnetic field, right? So there cannot be V. Then, if we turn on weak magnetic field, which corresponds to something like this here, what we have is that the Stokes I doesn't change significantly, but some part of the Stokes Q is rotated into the Stokes U, and overall the amount of linear polarization decreases. But the magnetic field is still weak enough that, that there is no appreciable Stokes V. And I'm going to show you later some profiles from the real objects, from the solar prominences, and you're going to see that it's really the case, right? And then finally, when we have the strong magnetic field, where the Zeeman splitting is greater, or at least comparable to the Doppler splitting, or at least significant high enough to create Zeeman signatures, then we're gonna, it's never gonna truly happen, but overall we're gonna lose the signatures of the Hanle effect, and we're gonna see this Zeeman regime where we see these profiles that have completely different signs. And we know that physics behind them is different. Of course, it's not different physics, it's just different regimes of one and the same physics. But it's easier for us to understand and to track this if we split them in these, you know, regimes like this. Okay, very good. And then from there, and now we're going to get into some really mind-boggling things, is that what people like to do, they like to create these polarization diagrams. Okay, and the polarization diagram is this sort of, well, a diagram, right, which shows you how for, so obviously there are 3 main, the vector of the magnetic field is going to determine how Q and I are going to behave, right? And what this diagram, this particular diagram here, what it tells us is that for a fixed, so for fixed inclination of the magnetic field, so one orientation angle is being fixed, then the full lines, each of the full lines corresponds to each of the full lines corresponds to one fixed azimuth of the magnetic field. So you can see numbers here. And then different values of the magnetic field are along these lines here. And they result in different values of I and of Q and U. Okay. And the dotted lines are for the constant values of the magnetic field, right? And changing the azimuth and getting different values between the different values of Q and U. Okay. So basically what I do is I fix magnetic field to, for example, 1 Gauss, okay? And then for the, so here is 1 Gauss. For the inclination of 0, okay, I have no U, okay, but I have some Stokes Q, all right. If the magnetic field was 0 Gauss, I would only have Stokes Q and it would be here at the top, already at 0.1 Gauss for this specific line, my Stokes Q in the case of zero azimuth is substantially decreased. Okay, and you see as I'm increasing the magnetic field, so let's just focus along this vertical here now, which is for azimuth equals 0. As I'm decreasing the magnetic field, my linear polarization is decreasing, but it's not decreasing linearly, right? At some point it saturates, and this is what we call saturated Hanle effect regime. Okay, you see now, let's for example focus at what did we do? 1 Gauss is here, right? 1 Gauss changing the azimuth changes Stokes I and Q, Q and U according to this line here. Okay, and what I want you to stress here, okay, is that there are going to be some combinations where I'm gonna have, and of course we can't see it from these sketches here, but I'm telling you now, and trust me, I'm gonna show you examples of that later, is that we're gonna have some points where for different combinations of angles and the strengths of the magnetic fields, we're gonna have same Q and U. And that's going to be very, 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 very problematic. And that's something that is called ambiguity. Okay? And I'm going to show you an example of ambiguity very soon. And actually, the reason why these ambiguities exist is because they exist in the Hanle effect equations, exactly. So if you were to write this matrix here, which depends now on the angles of the outgoing radiation and the whole magnetic field. So this, let's just make this explicit. So this theta and phi are the angles of the outgoing radiation. So these are these, theta and chi. And this magnetic field contains both the strength and the orientation of the magnetic field. Okay. So once again, when you write this full equation, which contains the magnetic field and everything, you can see that if I change inclination to pi minus inclination, and if I change the azimuth to its negative value, this combination on the right is going to have give the same combination on the left. And there are also two additional degenerate variants between which also take into account the strength of the magnetic field. So in principle, for Hanle effect, there are 4 different combinations of the angles and the strengths of the magnetic field that produce exactly the same polarization, not only in Q and U, but also in Stokes V. And very often, people are going to say, are going to mention this Hanle ambiguity or something called one black angles and things like that, and these angles correspond to this. Okay, to this degeneracy here. And the illustration of that degeneracy is given very well in this paper from Miranda from 2006, where they studied some ways to estimate, and we're going to talk about this much more now, about the ways to estimate vector magnetic fields in prominences. And what you see here in the full line and in the dashed line, which are basically literally overlapping, are 2 configurations of the magnetic field which have 2 completely different vectors. So different azimuth, different inclination, different strength of the magnetic field, and they're producing exactly the same Stokes parameters. And what we see here, I'm going to go into more detail in a sec, is the linear polarization. So first intensity, then linear polarization, and the circular polarization coming from prominence of the limb, which is an object that scatters radiation. So we see Q. So first we see emission lines because it's reflected light. We see Q and U, which are created obviously from the magnetic field, because there was some, if the absence of the magnetic field, we will see only Q. With the magnetic field, some of that rotates into U. And we see V, which looks like Zeeman because it is Zeeman. So there is some weak Zeeman signal in this case. Okay, so take some time to digest this, and because now what we're going to do, we're going to move to prominences and some other examples. Initially I wanted to make this much more about prominences, but then there were some examples from the chromosphere and so on, which I really wanted to show. So in the end, it's going to be a little bit of everything in this last half an hour. So what we're going to talk about is how we can employ all these things to model prominences, which are the objects of the solar limb, and to analyze their polarization. So first of all, let's talk a little bit what the prominences are, just a little bit. So here is the image of the corona that we saw before, and you see that corona is huge. It extends very far away from the sun. But very close to the limb, we see these little thingies here, right? And actually, if you could really take a look at them, this is obviously a composite image, but if you could compare the brightness of these objects on the limb with the corona, you would see that they're much, much brighter. And their physics in the mission sense is the same. And actually, I'm going to zoom into them right now. I'm going to show you some results of these things which are on the limb. They're relatively small, so you couldn't quite see them here because this was the image of the whole solar disk. But when we zoom into this, and by zooming, I mean observing it with the telescope, which has a small field of view, like the Deakist is going to have, we can see that these are some, I would call them sheet-like structures on the solar limb. So they're very interesting, right? They're sort of small. I don't know how big can they be, like a couple of minutes maybe, something like that. They're literally there above the limb, probably even smaller than a couple of minutes. I think that's an exaggeration. And we see that there's something sheet-like, and they have a lot of structure there, right? And they have been observed for quite some time. They observe them. People try to observe them from the ground. IRIS observed them. They're very interesting. They're very interesting objects. But they are, for the most of the radiation, they're not emitting their own. They're actually scattering the radiation that is coming from the photosphere, right? And one way to understand this is that to model them as some sort of a slab that is hanging there above the, so each pixel of the prominence you model as some sort of a slab that is hanging there above the sun. The radiation is coming from below and from the sides. It's being scattered there, and obviously the prominences are illuminated anisotropically. Then, as you're going to see, there is some magnetic field that breaks this isotropy with respect to z-axis, so axis symmetry around z, and it creates some anisotropy there, and we see these prominences having polarized light in both Q and U. And in order to understand this well and to model this well, we need to know the height of the prominence above the limb, or the emitting chunk of plasma above the limb, because obviously the higher it is, the more anisotropic radiation is coming to that. And there is actually another interesting effect, which I can't talk about now, but if you ask me, I will be happy to talk about it, is something called Doppler dimming and brightening, which is a very interesting aspect of line transfer, where the spectral line of the moving medium sees more or less of the incoming radiation than it would be if it was standing, right? And most of the prominence spectropolarimetry studies are working with this famous helium-10A30 line. Some of you are maybe already familiar with that. In February, we had Andres and Ramos visiting NSO. It seems like it was 10 years ago, and we had this workshop talking about Hazel and Hazel 2, which is the code for modeling these things. So helium-10A30 is a line that that arises between these two levels, so 2s3 and 2p3 of neutral helium. And this lower level here, it's not the ground level of helium, obviously, because it's 2s3, right? And helium only has 2 electrons. So it's one of the higher levels, which is, as we would call it, metastable. And metastable means that when, for some reason, electron ends up on this level 2s3 here, it takes a lot of time for it to de-excite down there. So we were talking about Einstein, we know that it's the Einstein coefficient of emission that determines this, and we talked about some very large values. So for this, it's something much, much smaller. I don't know the exact number.
Ivan?
Yeah.
Was this transition 7065?
I don't know. What do you mean?
Like, is it observed on the sun?
I don't know. Maybe somebody else knows. Kevin, Jana, do you maybe know? We can look it up. Yeah, we can look it up immediately after the class. We can just go to the archive. We can see how strong the line is and see how it looks like. I don't know by heart really.
So there's no rule that's breaking between the two levels, right, to make it forbidden.
No, it's not forbidden. So all the dashed lines are the allowed radiative transitions. So it's going from S to P level, so it's allowed. So S and P correspond to angular to orbital quantum numbers, right? And we know that it cannot be from S to S or from P to P or from T to T, but from S to P it can. So it definitely exists. I'm going to stay online. I'm going to keep my screen shared, and we're going to take a look at it immediately after. So just remember the number 7065. But 5876 is observed, and that's the D3 line, right? Why does the lower level has no magnetic splitting? Well, it does. So Aline asked why the lower level has no magnetic splitting. In this case, it does. It's just that this theory that we worked before assumed that the lower level has no magnetic splitting, which would mean that the J is equal 0 for that level. For example, for strontium 4607, the lower level has no splitting. This one has magnetic splitting. So helium 10830 is an example of the spectral line where both the lower and the upper level are polarized. So you have to use the density matrix formalism to model it properly. And that's the reason. Okay, so I'm now running a little bit ahead. I'll come back to that. I'll mention this more. So what I want you to note is that the upper level of 10830 is actually three levels, one with J equals 0, one with J equals 1, one with J equals 2. So what we actually have is three lines that constitute 10830, and these three lines are, that's why whenever you plot, and two of these are blended, so actually this dashed line should be three dashed lines. And then each of these lines in the presence of the magnetic field splits in more sublines, okay? So these three lines are not because of the Zeeman splitting. These are simply three lines which belong to the same term, but have different angular quantum numbers, okay? And they're very close to each other in the spectrum because helium is very simple, so they're very close to each other in terms of energies and wavelengths. All right, so how does this helium 10830 emit? Well, it emits because, as I said, the lower level is, as we call it, metastable. So after, let's say, some recombination processes, which occurs due to the presence of the ionizing coronal radiation and things like that, we have a lot of atoms that end up in this lower level here. And then the incoming photospheric radiation at these wavelengths of roughly 10830 can scatter in this transition here and create, and we have the similar scattering polarization as we talked about in the previous class and this class. Of course, it's, as I said, it's more complicated because now you can't use a simple scattering matrix to describe that because you have both the upper and the lower level that are polarized. So you have to go all the way and calculate these radiation field tensors, density matrix, and so on, and calculate the emission processes and the absorption processes of your medium, taking into account everything, okay? It's a bit more complicated. All right, so what we actually do is that, the way we model this line, we can't model all the detailed physics now to take into account everything. So what we do now is we say, well, okay, you know, some amount of the atoms is going to be in this lower state here, and that amount of the atoms is basically going to set my opacity in this line, right? We know that the main contributor to the opacity is the population of the lower state, and that is going to be all contained in this quantity called optical depth of this slab. So if you remember, we were modeling it something like this. So we had this little blob, or here it's the cube, and then we were looking along the line of sight here, and then the main one of the two main ingredients which determined how much radiation we are getting was the optical depth along the line of sight. And that optical depth is going to be free parameter of our model, right? Then the other big thing that is sort of, you know, delegated to one component is the shape of the absorption and emission. And that is determined by the three quantities with the position of the line center, which basically determines what's your line of sight velocity. Doppler width, which is the broadening of the line, and the damping, because we know that our lines are not really Gaussian shaped, that they're more like Voigt shaped, right? And then on top of that, there is the magnetic field vector that permeates this cube here, And finally, in order to calculate precisely the anisotropy of the radiation that is falling here, I need to know the height of this thing above the sun. Because higher above the sun I am, the smaller the cone is where the radiation is coming from, and the anisotropy is going to be higher. Okay, cool. So so I think my earphones might be running out of battery. I'm not sure what this sound means. So if you ask something and I'm not answering, just type it up. I have the chat opened on another window. Okay, and then people use that. And here is another example. And this here is where we're going to go in a second and talk about the fitting. What you see here is an example of a prominence spectrum seen in helium-10-830. And what I want you to do now is to take maybe 30 seconds, 45 seconds, 1 minute, and I want us all to think about why all these Stokes components have the shape they have. Okay, so I'm going to talk a little bit about their about what we see here. Actually, you use that to think about it. Then I'm going to shut up for a little bit so we can all think in silence, and then we're going to discuss what we see here. So what we see here is an emission line, okay, which is an asymmetric. Okay, remember that 10-830 has 3 components. Okay, so it's an asymmetric emission line. So one of the things that we need to understand is why this is an emission line. So we sort of have a good idea why that is so. Then we have Stokes Q, okay, which has simple shape like this. Stokes U, the opposite sign, similar shape. And Stokes V, which almost doesn't exist, right? This is 1 pixel of the prominence. Okay, or maybe a few pixels added together, it doesn't matter so much. Okay, so this is a small piece of a prominence observed, and this is the spectrum. Completely different to what we see on the disk, in the atmosphere. So this is something completely different. We talked about the formation for quite some time now. I will shut up now, and I will give you a chance to think why these look like this. You don't have to wait for me. If you have some remarks, you can speak up, you can write in chat, something like that. Okay, so there were 40 seconds. Any conclusions? Any remarks? Any? So I mentioned some of these things along the talk. It's nothing. I don't expect anything very deep. Just a brief nod of understanding what happened. Okay, I'm not going to torture you so much because scattering, polarization, and radiative transfer are torture on their own. So here are the some things that I would notice. So first of all, what we have here is the line scattering on a slab that is optically thin. So we see the emission line because the source function is determined by the amount of the incoming light, right? But the optical depth is higher close to the line core and weaker away from the line core. So we see an emission line which emits the most in the center and less and less when we go toward the edges, right? Or in a way, you could think about it that we have the emission coefficient, which is set by the population of the higher level, right? And then it just behaves as the emission line, but that population is set by the incoming radiation. You can also think about it that way. Okay, and for this specific line, 2 components are blended, and this is what we call red component. Yeah, Aline, that's a very good remark. Yeah, I mean these are still not percentages, but they're still very small. Yeah. So what we have here then is the Stokes Q and U, which look the way we would expect them. Note that polarization, which corresponds to the blue component, is almost gone, right? We almost don't see it, but we see some polarization of the Stokes Q. And the reason why this is almost gone is that this intrinsic polarizability that I talked about earlier is different for the blue and for the red component. Okay, and what is happening here is that since prominences are sitting very close to the solar limb, the anisotropy that they see is not that high. Okay, and in addition there is magnetic field, and in addition there are other processes, and there is intrinsic line polarizability, and so on and so on. So what we end up with is the linear polarization that is not so high. It's 1% or less. But now have a look at the circular polarization. Circular polarization looks a bit, if you really use your imagination, it looks a bit like some hints of, you know, Zeeman effect are there. But since the magnetic field in prominences are so weak, we see very, very small hint of the Zeeman effect here. Right, but still we see it, and still we can use it to help us constrain the line of sight magnetic field. Right, pretty cool, pretty cool. If you were to look at the whole map of a prominence, and here this is the paper from David Orozco Suarez and the collaborators from some 5-6 years back, where they did the map of the prominence and then the inversion, which means the analysis of that map, the interpretation if you want. And here is what we see how the integrated Stokes Q, U, and V, integrated meaning integrated along the wavelength, look like, right? And you see that basically Q maps where the prominence is. So if I showed you the image of the prominence, it would look very similar to this Q map. And the reason is very simple. It's because we are mapping the amount of Q. And even though the fractional polarization might not change much, simply where I have more of the plasma, I'm going to have more of the signal. But now Stokes U shows you how the magnetic field is rotating this, right? So where the Stokes U is 0, there's probably no magnetic field, or it's really oriented in a way not to do any rotation. But here where I have a lot of Stokes U, it means that I have conveniently oriented magnetic field to rotate some of the Stokes Q into Stokes U. And finally, I have the Stokes V, which tells me where I have the strong line of sight component, right? Okay, and now what we can take a look is what these people did. What these people did is now they took this model that we talked about, they took Hazel, they analyzed each pixel of this to produce the map of the physical parameters of the prominence, the same way that we do for the photosphere. And here are some of the results, right? So we get the maps of these parameters, and what I want you to stress is that here in this model, some of the parameters don't have clear physical meaning, and I would call them nuisance parameters. And when I say a real physical meaning, I'm not saying that the physics is wrong. It's simply that we don't know how to interpret them. Like, for example, this optical depth that is used as a free parameter in the inversions is, as I said, it depends on it's simply determined by the population of the lower level, but that population of the lower level is influenced by so many physical processes that we don't know how to disentangle that, how to make that, how to make some sense of that. So what you see here is simply you can see where the prominence is more or less opaque, and actually the map is very interesting in that context. But we can't understand anything from that. And the similar is for the Doppler width. So simply the Doppler width tells you where the lines are more broad and less broad. And if I may notice, it seems like the places where the optical depth is smaller coincide with the places where the Doppler width is higher, right? So that's an interesting one. But we know that there are so many processes entering the Doppler width of the lines, like turbulence and other stuff, and maybe some more large scale, movements. So prominences are really, really cool. There's a lot of amazing physics happening there. And I'm not a solar physicist, so I don't know exactly what physics, but I know it's super cool. And also, like, to disentangle these maps of the Doppler width is amazing, but probably impossible, right? And finally, the line of sight velocity, that tells us something. So that at least tells us how the plasma is moving in the prominence. And there was an amazing paper by Marianne Martinez-Gonzalez and collaborators, where they looked at the feet of the prominence, and they saw from the Doppler velocity that the feet are rotating, I should have put that here as well. I apologize. That's a really cool paper. I will put it in the lecture notes after this. By the way, for the previous class, I have put quite contrary to usual. I have put a lot of PDFs for reading about polarized radiative transfer. Okay, nice. But now when we look at the magnetic field of the prominence, the map is going to be ambiguous. So let's unpack what we have here. The upper two panels are the magnetic field strengths. The lower two panels are the inclinations. And here they found, as in the previous, as in this slide, where they found two, so as in this slide, where we had two orientations and two strands producing the same results. That means when you do the inversion, you should get two answers, okay? So being very responsible and detailed people, they noted all these two answers and classified them and showed us these two maps. And what you see here is that there is not one map. There are two maps, and here is the field strength, here is the inclination, here is the azimuth, and they're all completely different. And here is the projection of the magnetic field in the plane of the sky, and it looks different. So there are simply two solutions, and there are two more, which we just, with additional rotation, that are completely compatible, and we can't decipher them. And that's something that is very, very interesting, right? And what you see here is actually that you have one map that has lower magnetic fields, one map that has stronger magnetic fields. Inclinations are different, azimuths are different, and that's it. And these ambiguities are not there because of the noise. So those of you who already meddled with some inversions might, and I mean, you might have figured out also from our hands-on that if you infer a line of sight magnetic field, that if you, for example, see a magnetic field with line of sight 500 Gauss, it could be 500 Gauss magnetic field which is directed toward you, or it could be 1500 Gauss magnetic field that is very inclined with respect to you, and you only see the 500 Gauss component. So yeah, on the disk we had and that was and on the disk observations, these kind of ambiguities don't come from the equations, they come from the noise. These ambiguities here come literally from the equations, and they are, strictly speaking, unresolvable, although we can think about ways how to do it in a more way. And there are more more subtleties to this. Strictly speaking, there are four degeneracies which are completely indistinguishable because the spectral lines here are in something called saturated Hanle effect, which means that magnetic field is really strong, and basically critical magnetic field for this line is 0.1 Gauss, and here we are getting tens of Gauss, and so on and so on. So there's much more to this. I'm sort of running through this, right? And another interesting thing is that we can look at these prominences from above. So if you look, sometimes you might have seen these, dark snake-like features on the sun, and these are something that we call filaments. And we think, so maybe this is a very extreme example, but sometimes we see these really small things on the disk, and they really look like the prominence is seen from above, right? And when you look at the spectra, they are also seen in helium 10A30, but the helium 10A30 now looks a little bit different, okay? And what you see here is, again, filament spectrum in this case, right? And the filament spectrum now, because we are looking at this on the disk, we see the lines that are in absorption and not in emission. Can somebody tell me, from the radiative transfer point of view, why are the lines in absorption and not in the emission? Like from the point of the radiative transfer equation, let's say. It's okay. It's not going to be in the homework. You can just make wild guesses and speculations. Okay, maybe I'm making you very sleepy with this. Cool gas or hot gas? Yes and no. So I prefer Dennis's answer that the source function is decreasing. Very good. The source function in the filament is determined by the incoming radiation. When I average, because the filament is illuminated by some cone, that source function is going to be smaller than the incoming intensity, and I'm going to see that as an absorption line. So the fact that it's cool gas over the hot gas isn't necessarily the answer, because in principle the temperature of the filament could be higher than the temperature of the photosphere underneath. So keep in mind that it's not the filament that is emitting; it's scattering medium. Okay. And here we see something again. We see now the optical depth of the filament is different. So we actually see the linear polarization in Stokes Q as well. And note the different sign. The different sign is because this intrinsic line polarizability is negative. So we have negative linear polarization. We have the opposite side on linear polarization with respect to the the red component. Magnetic field has such an orientation that Stokes Q is almost zero, which is very interesting. And here you now finally clearly see that we have some weak Zeeman signal again. But again, the Zeeman signals here are much weaker than the Hanle signals. I strongly recommend reading this paper. You can't see the reference. It's Sensi Ramos, Trujillo Bueno, and Landi Del Innocenti, 2008. I will also post it on the webpage, which really shows amazing examples for all the cases. So you have prominence, spicule, filament, active region filament, emerging flux, sunspot, and you have 10-30 for all these things. And it's really, you can really appreciate the difference in physics of the line formation in all these cases. Fantastic. So for those of you who are interested, there is this Hazel, and actually now Hazel 2 code, which is free, publicly available on GitHub. It's developed and maintained by our friend Andres Asensio Ramos. Hazel stands for Hanle and Zeeman light. So it's intended for modeling and inversion of helium lines, namely helium 1030 and helium D3, which is helium 58 something. And it has a very, the atomic physics there is very complicated and very complete. So it all follows the density matrix theory from Egidio's book. From there, it means that, and since the prominences and filaments are so complicated, it actually means that in order to extract something, we need to use relatively simple models. So we presume that we have the slabs, and that these slabs are permeated with magnetic fields, and that they're scattering radiation in this very simple way that we sort of studied now. And you can calculate calculate IQUV, or you can just feed it observations and obtain all these parameters. And so far it was applied to prominences, filaments, active regions, flux emergence, sunspots, stuff like that. And there are even some people who are using it to model extrasolar stuff, so like radiation of the disks around stars and stuff like that. And actually, in our level 2 pipeline, we plan to use Hazel 2. And one of the things, so of course, we're still not sure whether that's going to be done by the default, but in principle, since around helium 1030 in the spectrum, you have more lines, and some of these are not formed in these blobs and prominence filaments, but in the photosphere underneath. So in principle, there is Hazel 2 even has the capability of inverting photosphere and the slab parameters simultaneously. So when we talked about photospheric inversions, we said that, what we want to know is the stratification of the temperature, line of sight velocity, and the magnetic field vector on the optical depth scale. And then in addition to that, photospheric radiation, that photospheric radiation now passes through this slab, which is parameterized by some other components. So optical depth, line of sight velocity, magnetic field, and so on. And then it finally leaves the slab, and we see that radiation. And then we invert it, so we obtain all these parameters here. And I'm just going to show you a hint of some of the things that I have recently prepared. And hopefully, if we have next time, we can look at the other parameters next class. Here is the depth stratification of the magnetic field from sunspot observed in 1030. And so basically, this magnetic field in the photosphere, and then at the optical depth -1 and -2, comes from a nearby silicon line, which is, you could say, something which is formed in the photosphere, upper photosphere, maybe temperature minimum or something like that, and the very smooth and weak magnetic field extracted from 1030, but simultaneously, so fully consistently. And I want to say, just, don't cling on this too much. So some things here make sense, like for example, you can see that the magnetic field at log tau equals 0 is much sharper and more well-defined than the magnetic field at -2. But for example, at the very core of the sunspot, these magnetic fields are strong. We have some strong magnetic fields here that are stronger than in the deeper layers. So I don't fully understand why that is. So we need to work more on this. I mean, I need to work more on this and to make more sense. But these are very cool. These are very cool things to observe and very cool things to work with. So yeah, if you're interested, we can talk and do something together. Right, so to recoup these things, and then I'm just gonna run in a few minutes through some more complicated stuff, is that what we started from here is that the vertical anisotropy creates some Stokes Q, right? And then the magnetic fields, in a way, rotate some of that Stokes Q into Stokes U. And there is a full theory, which is density matrix formalism, which completely takes into account the interaction between the radiation and its anisotropy and the level structure and the population of these Zeeman sublevels. And one thing that naturally stems from here, and that I already mentioned last time, and I told you that if you like it, you should also talk to Niraj more because he's working on that, is that the radiation doesn't have to be axially symmetric. So one assumption here was that the radiation, the intensity, the incoming intensity was axially symmetric, so it created no Stokes Q, but it doesn't have to be. And here is a very simple toy model where we made a slab which was very simple. It was basically just a series of blobs. And what you see here is a simulated slit. So this slit illustrates how the intensity, Stokes Q and Stokes U, are changing along the slab. And obviously places where the intensity is higher are places where my optical depth is higher, thicker. And where the intensity is lower is where my slab is more transparent, right? But what we did here is we allowed the pixels in the slab to talk each other. We allowed the photons to scatter, for example, once and then go away and scatter along the other, sorry, and then to scatter around. So, and we also calculated fully the azimuthal, let's say, anisotropy because of that. And here you see that simply because of these geometrical things, because our slab is inhomogeneous in space, we have some Stokes U arising, right? Okay, and simply the sign of that anisotropy is different on the, of course, here the box has hard boundaries, so you see these things at the edge here, which shouldn't really exist, but it doesn't matter, right? But you see that even as I go along the slab, I have this positive and negative linear polarization in Stokes U, right? And I have shown you some more sophisticated and more realistic results in the last class, which was the scattering polarization in strontium 4607, calculated from a Murray cube. And here we see that since Murray cube is inhomogeneous, the radiation coming from different azimuthal angles is not the same, because, for example, when you are here at the edge of the intergranule, from one side there is hot radiation coming from the granule, from the other side there's less radiation coming from the intergranule. So what you would see after that is you would see some structures in Q and U, even looking at the disk center. If you remember before, we were taking a look at, we said that at the disk center at mu equals 1, there should be no linear polarization, right? And this strontium 4607 is also a magical line. So if you're into radiative transfer, we could talk about it more. It's a super well-behaved line. It's something called normal Zeeman triplet, which means it's exactly this cool example where the lower level has J equals 0. So it's unsplit. Upper level has J equals 1. So it's split in only 3 subcomponents. Scattering polarization is, in this case, is relatively easy to calculate. You can use the scattering matrix formalism that I have shown you, so it's relatively straightforward to calculate. The line is formed in the photosphere, but it has very large Einstein coefficient emission, Einstein coefficient of emission, which means there is a lot of scattering. And it also means that it's sensitive to relatively stronger fields when we talk about Hanle effect. So it's not easily saturated, and it produces relatively high degrees of polarization. Okay, so what you see here in this paper by Tanausu, Delpino Aleman and the collaborators, you see something like percent or 2% even. Probably this is degraded significantly when you take into account instrumental effects, but still, this is something that we hope to see with DKIST, and this is going to be a discovery, right? Okay, Yeah, very quickly, I won't talk about this too much. I just want to say that for some lines, like for example, calcium 8542, which some of you are also very interested into it. In some situations, the signals coming from Hanle effect and scattering polarization can be comparable with the ones coming from Zeeman effect. This here is the famous simulation, famous Bifröst simulation of enhanced network calculations done by Yuri Stepan and Javier Trujillo Bueno. And you see that for calcium 8542, because it's strong and it doesn't have a very large lambda factor, the Zeeman signals are not that strong. So, I mean, the line is strong, the line is broad, and it's really broadened. So Zeeman effect weakens, and it becomes comparable to the Hanle effect. So this is also amazingly interesting result and amazing project. And this code is now publicly available, so-called port. So, okay, we are here at the end of today's lecture. So what I want you to remember, even if you completely forget about the scattering and scattering polarization, is that scattering polarization and Hanle effect are direct consequence of the scattering, and they are essentially non-LTE, which implies complicated modeling, but we can get some insight by just imagining it in some classical way. And the polarization patterns are fundamentally different from Zeeman ones. And the sensitivity regime to the magnetic field is much different because it's determined both by the lambda factor and by the Einstein coefficient of emission. If you remember, in Zeeman effect, we only had lambda factor as the important thing. The problem is degenerate for the interpretation, so I don't know if we will be able to know a true magnetic field orientation for our prominences. Probably we need to constrain it using some physical considerations. It's not only visible in prominences and other off-limb things, it's also visible on the disk. And again, not only in helium-10-830 blobs or clouds, it's also visible in your good old photospheric and chromospheric lines, such as strontium 4607, such as calcium 8542, such as calcium 4227, such as H-alpha, etc., etc. And there is a lot of results that I didn't have time to talk about. So if you're interested into this, look into CLASP rocket experiment, look into magnesium H and K polarization observed by one of these old missions, etc., etc. Okay, this is everything that we had for today. Questions, comments, critics, remarks? Okay, I'm not going to bother you a lot because I presume that this might have not been interesting for everybody. You won't have any assignments from this, so I reckon no harm done, but I think it's good for you to hear this. I'm going to stop recording now. I'm going to stay online so we can take a look at this line together. And if you think about anything to ask me, just go ahead. Okay, thank you very much, and see you on Tuesday.